We saw last time that when a charged particle moves, it creates a magnetic field that loops around the particle's velocity. In most applications, we work with many charged particles moving in the same direction in a wire, which is what we call electric current. Any wire that carries electric current creates a magnetic field, just like an individual charged particle does. The calculation of this magnetic field looks very similar to that for a charged particle. We simply trade out the charge and velocity for the current in the wire and the length of the wire. Now, you can't just have a single straight wire carrying current off into nowhere, so we'll study a loop of current modeled as 4 connected wires. Here, we create the 4 wires for our loop. We call these wires the sources, since they are the source of the magnetic field vectors we're about to draw. Next, we create many observation points where we will display the magnetic field vectors. Remember, the magnetic field vectors exist everywhere. These are just the points where the field will be drawn. Finally, we set up a loop where we adjust the size and direction of each magnetic field vector based on the current in the loop. The resulting visual shows how the magnetic fields from each wire in the loop combine to form a sort of double loop, similar to the electric dipole that we saw earlier. This pattern looks suspiciously like the magnetic field created by a permanent magnet, which is how we know that permanent magnets are built out of tiny loops of current at the atomic level. Of course, current isn't always constant in a circuit. In alternating current circuits, the current changes direction like a cosine function, which causes the magnetic field pattern to oscillate as well. You have now learned how to model the magnetic field of a set of wires. Follow the link in the description below to find a set of activities to help you learn more about magnetic fields.